even civil engineering, healthcare, and so on. Yeah, so my areas are mainly data matching. In this presentation also, for those who don't know, you'll be introduced to data matching, system software, which is about software infrastructure, and also intelligent systems, which covers artificial intelligence and so on. But all of these areas, they overlap anyway. There are lots of studies where methods in one area is in the other area. Okay, so title for my talk is Conquering the Challenges and Uncovering the Power of Large Data Sets. Could I just confirm how much time I have, Doctor?
Approx 1 hour, yes,
1 hour,
because
okay.
it's from 11 to 12. So I hope we can do a lot in that 1 hour, Doctor.
Okay, thank you. Okay,
Right.
right. So conquering the challenges and uncovering the power of large data sets. Okay, so these days, artificial intelligence is about learning from data, coming up with data-driven solutions, and these methods are used in all areas, not only in computer science, engineering, mathematics, and so on. But there are problems with handling large data sets. So in this talk, I give an overview of issues of large data sets. We look at understanding large data sets, and then several approaches to conquering the challenge of handling large data sets. Then towards the end, we look at applications and opportunities in these fields: data matching, system software, and intelligent systems. We look at opportunities for using data for breakthroughs in these fields. Now, I do understand that some members in the audience, they are maybe part of a PhD program related to water, civil, and other related areas. So I know the audience, some have already started on their research. So you would be aware about some of the issues, but hopefully you'll encounter some new information that will help you with your studies or think differently about problems that you are trying to solve. So in the era of big data, it's very crucial. Artificial intelligence, for example, traditionally, it's now what is called classical artificial intelligence, which had to do with generating data structures known as trees and searching those trees, looking for solutions. Nowadays, things are moving more towards data-driven solutions, where we build models that learn from data to solve problems. Now, it is really difficult to solve some problems by specifying an algorithm for the computer to follow. For example, it is difficult to get a computer to drive a car just by following an algorithm, because the algorithm will be very complicated. There are so many things to consider when driving a car. You know, the other vehicles on the roads, different types of vehicles, the road markings, the stoplights, roadworks, pedestrians, buildings, potholes, things like that. So what happens is an algorithm is not specified for that, but rather a machine learning model is used to observe how human drivers drive and learn how they drive. So as the humans are driving, they are generating data, and that is learned to now drive these cars. So we have the self-driving cars. Okay, so that's also known as automatic programming, where we can produce a program automatically without specifying an algorithm, simply by training a model. So there are challenges, though, in handling, processing, and extracting meaningful insights from large data sets. But the data sets have enormous potential. The issues, though, around for example, storage. If you've got so much data, where do you store it? Your typical laptops, the storage, what is common is maybe half a half a terabyte or 1 terabyte, not more than that. But if you have got a lot of data that cannot fit there, then what happens? Then you have got to look for other resources. Also, when you have a lot of data, if you are training complex models, for example, then also with lots of data, it has implications on computational resources. So just, a single computer might not be sufficient. You may need a whole set of computers to build your models. Also, data comes into even network communication. When there's huge amounts of data, there could be high latency in communicating from one computer to another computer. So if you are solving a problem using several computers at the same time, to speed things up, but your network is slow, then that will slow everything down also. So in this talk, we look at intricacies of large data sets, obstacles in handling them, and we look at these applications, and the data matching, system software, and intelligent systems. So large data sets, we are introduced to the 5 V's, which characterize large data sets. We have got volume, velocity, veracity, value, and variety. So volume, as I said, the sheer size of the data, how do we store it? There's so much data. Maybe we are dealing with images, or we are trying to index the whole internet. That's huge data set. How do we store that? Velocity, the data is being generated very fast. Veracity also. Data is imperfect. That means there could be missing data. There could be, certain values that are missing, or there could be lots of noise in the data. Value represents potential insights we can get. And variety, the data we are dealing with could be coming in different formats. It could be a mixture of structured and unstructured, structured as you might have in your tables, which you load into your data frame structures as you have in R and Python and so on, such as pandas, data frame in R. There could be unstructured, like we are dealing with web pages. Web pages have inconsistent structure. Different web pages have different structure. So that's also unstructured data, or Microsoft Word documents, PDFs and so on. This all unstructured data. So we have got the structured data, as we might have in relational databases, and then the unstructured dimension, or semi-structured, such as XML, JSON, and so on. So these 5 V's, they characterize the issue of big data and issues with big data. So what is this big data? How large does the data set have to be before you say it's big data? Well, or a large data set, there's no specific number. It's not about 1 gigabyte or 1 terabyte or 1 petabyte, for example. It is basically when you have a data of the size, according to these 5 V's, that negatively impacts the way you can handle the data. So if you are dealing with a data set and you want to do something on a small device that has little memory, little storage, maybe a laptop, then that is a large data set. It means you cannot process it on the resources you have. You now have to look for other resources to process the data. So those are large data sets. So it's not about a specific number, but about a quantity that starts giving you problems, the way you store the data, the way you process, the way you transmit the data, and so on. So we have these issues with large data sets. Okay, so these are the 5 V's again. Volume again, high amount of data, variety, different formats. Value, we need to get insights from the data, useful insights. Velocity is coming to us at a high speed. And veracity, inconsistency, uncertainties, imperfections in the data. So the sources, where do these data sets come from? Well, scientific research, as I believe members of the audience are doing, working with gene data, climate modeling, from business and finance, business transaction logs, for example, on e-commerce websites, customer transaction and so on, data from social media and the web, from Twitter, X, from Facebook, Internet of Things, where we now have devices that are connected to the network and they are producing data. these devices or things, they are all sorts of devices, even, your security door, your car, your refrigerator, your cooker. These ones, they are now all being connected to networks. They are producing data, and this data has got to be harnessed for business advantage, to improve the lives of people. We need to harness this data as it is being produced. So in harnessing this data, then we encounter these issues of storage, of computational resources required, and for network transmission, the bandwidth issues also. So we look at these approaches to handling large data sets. We have got chunking, streaming, data compression, sampling, use of databases, cloud storage, distributed computing, which includes supercomputing, high performance computing. We look at using efficient data structures also, code profiling and optimization. So chunking, we take a data set and break it up into smaller pieces in order to reduce the complexity, so that we can process the data in chunks, not together, which is a large piece, but in smaller pieces. So this is supported in data library like Python and so on. SQL now has support for that. Okay. So for example, we have document segmentation in natural language processing. Now, natural language processing is an aspect of artificial intelligence. It's a branch of artificial intelligence where we want the machine to work and reason with natural language, as you have with the chat applications and even information retrieval systems. When you search on the web, you use natural language to specify a query in Google, for example. So Google must understand to some extent your query in natural language, whether it is in English or whatever language, and then it has to act on that. So natural language, for example, documents are broken up into chunks so that they can be processed separately, as used in the more modern transformer models for machine learning. Streaming is another approach where we process the data record at a time. So if I've got 5,000 records, I don't process all of them in one go, but I go record by record. So there are some algorithms that work like that can be updated record by record, including neural networks, for example. And we have these frameworks such as Apache Flink and Spark that support this. So benefits: real-time processing, reduced storage requirements. If we are processing data record at a time, then we don't have to necessarily store all the data. Think of the way we watch YouTube videos, for example. The data comes in a stream. We don't, the video we are watching could be, 1 gigabyte, but we don't need to store 1 gigabyte. We just process the video bit by bit as it comes to our computer, and we watch what is in the video, and then we don't need that again. It's not stored anywhere. Okay. If we want, we can download, but we don't have to do that. Okay. So reduce storage requirements. Scalability, then we can handle more data. You can watch gigabytes of videos. You don't need to store on your machine. Of course, you need network that is fast enough. Stock market analysis, that's one application. In finance, we want to analyze the stock market. So we can do it in real time as buying and selling is taking place. We analyze bit by bit. We don't need to store the whole data for the last 100 years, for example. So chunking versus streaming. So chunking used for large static data sets, and it must be possible to chunk. Streaming is used for real-time or continuously generated data, live streams and so on. Of course, data compression also. If we have problems with storage, we can take a huge chunk of data and compress it so it takes up less space. So we can have the lossy compression where we reduce the size of the data, but we lose some information, as we have in JPEG, for example, your image format, which is originally used on the internet. I'm sorry, I think someone has not muted. I can hear some background noise. Please, could you mute? Okay, thank you. Okay, so we have got lossless compression though. We can actually compress data without losing information also, but not as much as the lossy compression. So benefits for that: reduce storage requirements, faster processing, faster communication. So we must also use the right compression method. Typically, if you are looking at video actually takes a lot of space. So it's already compressed, but it is possible to compress further. So normally the video will be decompressed as you watch it. We can also sample. We have a large data set. So because I don't have the resources to process the whole data set, I just sample records from the data set. Maybe I am, I want to, I want to detect fraud, for example. I've got huge data to detect fraud. I've got some transactions in the data which are fraudulent, some are not, right? But I don't have resources to process the whole data set. I can sample a balanced sample from the fraudulent, from the non-fraudulent. I can sample and then use that reduced data. So of course the benefits: reduce processing time, reduce memory usage, because my memory also will be less. The requirements are less because I'm not processing all of the data. I'm just sampling. So of course we need to make sure the sample size is appropriate and there's no bias. For example, machine learning, large set of medical images. We cannot process all of them. So we sample. Maybe we are looking at bone fractures. We have data set where we have images, X-ray images. Some are bone fractures, some are not. We can't process all of the data. So we can sample to make sure, for example, we get 50% images with bone fractures, 50% without bone fractures. But we must have an appropriate sample size. Now, of course, I mentioned storage requirements. When I say storage, there's what is called primary storage in the computer. Primary storage is the memory of the computer, which is RAM, which is where data is kept when it's being processed. Then there is secondary storage, which is what you typically have on your hard drive, whether it is your traditional hard drive or your solid state drives and so on. But when memory is limited, then we may end up even using secondary storage as primary, which tends to really slow things down. Okay, and that's why you find that modern laptops are suddenly very fast, much faster than before, because the sort of storage devices being used is no longer hard disk drives, but it's rather solid state drives, which are much faster. So it speeds everything up because the laptops, the computers, the PCs, they rely a lot on secondary storage, because that is where the files are stored, the data, the applications. So once your secondary storage is made much faster, then everything speeds up. That is really the bottleneck in most computers, the secondary storage. So data compression and sampling. So we can combine data compression and sampling for even greater reduction in storage, processing, network requirements. We can sample and compress also. Okay, so those are options one has. And of course, we have got the databases. Database can store data efficiently also and can retrieve efficiently. So that helps. The DBMS is the database management systems. For example, MySQL, PostgreSQL, we have got Oracle, and we have got other types of databases nowadays also. So they are designed to efficiently store data and retrieve them as they may be required. So for many users, it's good to use databases. And of course, when people study data science, they also study SQL, because when you implement a solution for data science, you typically want to use a database management system if your problem is quite large. Now for storage, you can also use the cloud. So we may not have enough resources, or it may not be practical for us to acquire storage devices. So we have the cloud resource available. Cloud, where we have computing resources available over the internet. That's basically the cloud. We can use cloud for storage, processing, applications, and so on. So the cloud, the benefit is scalability, because if we are doing our projects, you are working in, water resource management or whatever it is, you know, you may say, okay, let us buy 500 terabytes of storage. But later on, you may need more storage. It can be difficult to know in advance. But with the cloud, you can pay as you go. You know, there are no delays. If you need more storage, you can get it immediately. You just sign up for increased storage. Okay. It could also be cost effective. It could be cheaper than having your own physical storage devices. And it's accessible because it can be accessed over the internet, you know, from any part of the world. For example, Amazon S3, Google Cloud, Microsoft Azure blob storage. The only thing is when you're doing cloud acquisition for cloud, you must do careful cost benefit analysis because, you know, you have to keep paying. If you want to keep using the service, you have to keep paying. So in some cases, it might be better to buy your own locally located physical storage. Then it's yours. Then you can use it for as long as you want without paying anymore. But if you use the cloud, then you have to keep paying. Okay, but you have to look at the benefits as they are outlined here and do cost benefit analysis. Now, distributed computing frameworks. Now, having said all that, you know, the sampling and the compression and storage solutions and so on, but really sometimes we need more computing power. We can't process data on our laptops or even the PCs in our offices. So we have these distributed frameworks that can process data that's too large for a single machine. So we want to be able to do parallel processing because one issue is time. We need the results fast. So how can we speed things up? We can do things in parallel. If we are training a neural network, different paths could be trained on different machines so that things are done in parallel. Also, there's fault tolerance with doing things in parallel because if one component fails, the other components can continue. So there are these frameworks, Hadoop, Spark, Flink, and so on. Some I've mentioned earlier in the talk. So the processing and communication is critical. We want to process massive data sets. They could be too large for a single machine. So there are the software frameworks for that, but we also need the hardware. So the hardware, of course, we can have your regular CPUs, the server class, for example. You could, I'll soon get to our high performance computers or supercomputers. Okay, we need things like GPUs, graphical processing units, and TPUs, tensor processing units. These really help in deep learning applications. And when we need to carry out these operations, you know, that are coming from linear algebra, the matrix multiplications, dot products, and so on, that is where these ones shine, the GPUs, the TPUs. They have so many cores. The cores are much more simple than the cores in your regular CPU. They just do these basic operations, dot products, and so on. So the GPUs, they accelerate the matrix operations. Used in numerical computing as well as deep learning. The TPUs, they are targeted for deep learning specifically. In fact, they are developed by Google and they are used for the TensorFlow Google framework for machine learning and so on. Now, having said that, these high-performance computers, in the University of Botswana, we have high-performance computers, two systems. These are from decommissioned supercomputers that are coming from Texas Advanced Computing Center in the USA. So they decommission their supercomputers every 5 years. And, you know, they make available kindly the different components. They donate them to different universities. So we have, you know, one system based on Ranger from TSCC, Texas Advanced Computing Center. So Ranger, you know, for supercomputers, there is a ranking which is updated from time to time for the 500 fastest computers in the world. And this Ranger was one of them at one point, some years back. So we have some components there. So these high performance computers or supercomputers, they do things very fast, not because their components are so much different from your laptop, but because they do things in parallel. So if we are training a neural network, instead of using, you know, maybe you have 8 cores on your laptop, 8 processing units, which you might find commonly in modern laptops. Instead, you could have thousands of them, thousands of cores, and then things can be done in parallel. So the speed comes from parallelism, not because the CPUs are very fast. Having said that, the CPUs normally used for the supercomputers, they are server class, so they are quite fast and they have good quantities of good attributes for performance, such as cache and so on. So they are good performance. So we have the system in a dedicated room. It has its own power supply, and it has, so it's basically made of dozens of these computers put together on racks. There are over 100 of these computers that we have put together on racks, and they're connected together using fast network. So here the network is spelled out there. The 1 gigabit Ethernet and 10 gigabit Ethernet and so on. We have the computers themselves. They have the 27 terabyte storage. They are Intel Xeon computers. Clock speed 2.6 gigahertz. The computers themselves have 16 gigs RAM, and then we have the storage also, which is 300 gigabytes times 2, and then we have got lots of these 1.2 terabyte storage systems. So these are hot pluggable, meaning that you can unplug the hard drives from the system even without shutting down the system. Okay, so we have got 24 nodes on one rack. So we have got these racks. These are like bookshelves, as you can see here in this diagram. So this is the range as it was in the TSCC. So we have got these racks, the bookshelves, and inside we have the computers on the shelves. Okay, so we have 24 compute nodes in one rack, and we have got quite a number of these racks. So that's one system available in University of Botswana. We are trying to acquire more high performance computing systems. So I suggest, if you really need high performance computing resources to process large data sets, is either to acquire these parallel computers, because that's what they're, parallel computers, yes, that could help a lot. So for this one, these research institutes like in the US, they just give them away for free. They don't charge for them. So one might look into that. Yeah, they don't charge for them. The only thing is you might have to pay for shipping costs. Another one we have from TSCC also is Stampede, which is a more recent one. Again, it has its own dedicated room. It has got 11 terabytes of storage, and it has got, we have about 40 nodes there running these systems. The operating systems is CentOS, and we have a scheduler. So in each node, there's 16 cores, 32 gigs RAM, and 250 gigs hard disk drive. Now, these are shared resources. When you have a supercomputer like that, it's not meant to be used by one research student, for example. They are shared. So normally, when you have developed your software that you want to run on these systems, you submit your systems to these computers as jobs, okay? And then there's what is called a scheduler. The scheduler will decide when your job is going to run and for how long it's going to run and so on, whether there are restrictions on it. Then it will distribute your work to as many nodes or computers as you require, so that again you can process your data in parallel. Then it's much faster than running on a PC in your office. So Stampede looked like this when it was at TSCC. So it was quite huge. So we have parts of it. So that's our high performance computer. Okay. I don't believe we have any users for our system from outside the country, but the other systems in South Africa, South Africa, you have the Center for High Performance Computing. Now, we have also used those systems. They have a supercomputer known as Lenhao. This has got more than 1,000 compute nodes. It has got some very large memory. It has got the GPUs we mentioned, and it has got lots of file storage also. So the Center for High Performance Computing, they have agreements with certain universities. I don't know whether NUST is part of the agreement, but if it is, you should find out. If it is, you should take advantage, because then you can use their systems without paying. Just you can use them for free. You just have to request for a particular project that you want to run on them. Then you don't even have to go there. You just upload your data over the network, over the internet, and then you log in over the internet also, and you run your jobs and get the results back. Okay, so again, you just submit your jobs, then your jobs will be scheduled to run at a particular time. When the results are produced, you get them back to your site. Okay, so that's another thing that you could explore, the supercomputers at Center for High Performance Computing. So this one is, these ones were actually, they have some that were donated, but they have also acquired quite a lot for quite a good deal of money. So their systems are larger than the ones we have at the University of Botswana. This just shows the makeup for the compute nodes. They are Intel Xeons, 24 cores, 2.6 gigahertz, lots of RAM, at least 64 gigabytes. We have got some nodes with even larger RAM, 1 terabyte of RAM in 56, sorry, in the fat nodes. The fat nodes are the ones with lots of RAM. They have GPU nodes also, where you can do these jobs that require these matrix manipulations on the graphical processing units. So they have got lots of these also. This graphical processing unit, they are NVIDIA, that's the brand. Okay, and that's what Lenhao looks like as it is in CHPC. So apart from those parallel computers, fast computers, okay, what else could we do? When you're developing your software to process your data, you could use more efficient ways of processing the data. So there are certain data structures that work better. So this influence the sort of algorithms that can be used to process the data. For example, one can use dictionaries to look up values. You can use sets to check for membership, for example. There are arrays such as you find in the numerical Python library NumPy that are used to really work very fast with vectors. The implementation is very fast. So in the Python language, you have array-like structures known as lists, but those ones are quite slow. If you implement your system using lists, your program will run quite slowly. But if you use numerical Python, then those are optimized to run much, much faster. The issue around matrices, also there are data structures to store sparse matrices. These matrices, you know, they could be very large and most of their entries are zeros. So basically when you store the whole matrix like that, you are just storing lots of zeros, which just takes up space but doesn't help you much. So again, there are structures to store sparse matrices. So the benefits of all of these are just a few examples. The benefits, so you can explore more of these. Of course, I'm just giving you some suggestions. You can explore more on the internet to see which efficient data structures can I use and so on. So benefits, faster processing, reduced memory usage. So you need to look at the trade-offs for these ones. So dictionaries, for example, they have mappings like that where we have keys and values. So we have keys, values. So we want to look something up. For example, I want to look up, details about a student registered at NUST. I can just use that. I can use a key as the student ID and it will quickly give me the details about the student. Quickly, I mean in terms of a computational point of view. It says here O1 time complexity. When you are developing your solutions for, your water-related studies, environmental-related studies, then you might be interested in what is known as computational complexity, which is something coming from computer science. It just gives an idea for how long it will take an algorithm to run. But the algorithm to run is not specified in terms of seconds or minutes, because that is misleading. Because if I tell you that I have a fancy algorithm and it runs in 5 seconds, you may wonder, well, it may run 5 seconds on my machine, but on your machine, how long will it run? Okay. And then it's difficult to know exactly what 5 seconds means because it's tied to the hardware. But with computational complexity, then we look at this runtime as a function of the size of the problem, not as a size of, not as a function of the hardware, but the size of the problem. Okay, so a big O complexity is used for that. So it says here fast access, O1 complexity. That just means constant time. That means no matter how large your dictionary, no matter how many students register, it takes the same amount of time to get the details for the student. So these are desirable things when you're implementing. The issue of arrays, operations like dot product, you can see the relation, how many times faster if we use a specialized array implementation as composed to your basic arrays that you have in your programming languages. You can see that as the array goes up, the benefits increase quite a lot. From here, as the array size increases, so also the dot product time is much, much faster. So if the array is very huge, here about 5 million entries, you can see the size, I mean, if your array is at 5 million entry, dot product will take much less time, 140 times faster for these specialized libraries such as NumPy. So that's something to consider. Then the issue of the sparse matrix. You can see the matrix I'm talking about on the left here. It has got so many zeros. We are basically not storing anything. How can we store in a better way? So we can store, for example, in a structure like this, where we specify rows and columns, and then we only keep data about entries where the values are not zero. So that saves a lot of storage. So code profiling and optimization, something else you need to do. If you are implementing a solution and it's taken too long, what could you do? So most programming languages, the modern ones, they have what is called code profiling, where you can inspect your code as it is running to see where are you spending most of the time for your program. You may see that your program is running very slowly. So you may find that in a particular function, that's where most of the time is spent, a particular sub-program. So when you do that, then you realize, oh, it's actually my implementation of arrays, the one I'm using. So let me try to use a different implementation, and then you see the speed up. So optimization means you look at different solutions, you pick the best one. So optimization here, you want to speed up the code so it executes faster. So that's something else to try for your own implementation. So vectorization, for example, using NumPy arrays instead of loops. It is possible to even do a dot product using loops, but much faster if you use vectors such as NumPy. If you're using sorting, for example, it's better to use merge sort than bubble sort if you've got a lot of data. And we have memoization, which is about storing results of expensive calculations. So benefits for code profiling optimization: reduced processing time, improved scalability. You'll be able to handle more data because now you are taking less time for a particular data size. So you're saving time so you can handle more data. Now, applications for when we are able to conquer these challenges using some of these approaches that we have just looked at. These ones are just suggestions. There are many others, but if you are already advanced in your work, that's good. Hopefully, you saw a few points that you could learn from. If you are not advanced, that's even better. Maybe you picked up some more useful information there. Okay. So one field, we look at data matching. Data matching works like this. We have got two lists, two databases, and we want to see which record in the first database represents which record in the second database. So we are matching the records like that. Where is it used? For fraud detection, for example, to match transaction, to say this transaction was carried out by the same person as the other transaction, for example. Healthcare records. We have records coming from clinics. They were handwritten and then entered into the computer with mistakes, typos, and so on. Then we have got the records in the hospitals. We want to match which patient record in hospital is this, represent the same patient as which one in the clinical database. Once we have that information, we can better analyze to see this patient, if the patient, for example, sadly passes on in the hospital, which clinics was he visiting, what treatment did he get there, and so on. E-commerce and marketing, we want to know which customer on Facebook is the same customer as on Amazon, for example. We can match the records like that. So lots of techniques being used there. We can use probabilistic methods or even machine learning based methods used to do the matching. So the matching process like that. So you've got two databases. We need to prepare the data. Then we go to a process known as blocking or indexing. we need to compare the fields in the two records. So if I've got 100 records in the first database and 100 records in the second database, it means if I'm comparing all the pairs, I'm going to have to do 10,000 comparisons. Okay, that's quite a lot. And if I've got 1,000,000 and 1,000,000 in the two databases, then I've got to do 1,000,000 times 1,000,000 comparisons, which is a lot. So that's an example here. We really need to be careful how we handle the data, because the two databases could be huge. We could be dealing with people on the internet, which is huge. So when we compare fields in the pair of records, then we get predictions. We get to say this pair is a match or is not a match, and so on. And then we can evaluate the system. So here, for example, this shows two lists of people. So you can see here, you can see the A1, what is John Smith? John Smith, it says male, there's no prefix, and then there's the address, which is sorry, the street prefix, okay, like APT and so on. There's the street number, okay, and then we have got street name, street type, and so on. So for John Smith there, if you look at John Smith in the other list below, it looks like there's a mistake in the street number there. If they are indeed match, it's a mistake there. Okay, the street name is the same, Miller, but one says street number 42, the other says 47. Okay, so we want to match these records even though there are mistakes in them. So data matching is that, and it applies to what I'm saying, because this database A, database B, they could be huge. We could be dealing with so much data, so many records. How do we handle that? So the methods we discuss can help with that. Okay, so one method also, which I've not mentioned yet, is blocking. When we are doing data matching, blocking, that means that if I've got 1,000,000 records in the first database, 1,000,000 in the second, instead of looking at 1,000,000 times 1,000,000 pairs, I want to reduce the number of pairs I'm looking at. So I pick a field in the database and I say, if the records, all the records in the database that have the same value for the field will be put together in a group, and I'll only match within that group. So we have got blocking like that. How can we block? We could block on using postcodes, for example. So these are called blocking keys in data matching. Okay, so we could have blocking key value generated from surnames and postcodes. We could do that. There are all sorts of methods here used to optimize the process using, for example, soundex encoding, such that I'll convert Smith, the surname Smith, into the way it is pronounced, because I think, you know, even if there's a typo somewhere, the pronunciation will be the same, so then I can match like that and so on. So this blocking then helps me to reduce the number of comparisons to handle the huge data. Otherwise, the process could take too long. So blocking will be like this. So here, when we block, you see the pairs we are going to look at. So blocking key values for M600, there are two pairs we are looking for. For N250, there are two pairs, and so on. So I've reduced the number of pairs I'm going to look at by blocking. After the blocking is done, then we need to get scores. If I want to check A1 and B2, how well do they match? I'll generate a score using algorithms such as edit distance to see how similar the strings. So John and Janice, how similar are they? The score between 0 and 1, a real number. Here is 0.61. So they're a little bit similar. Smith and Meyer, and so on. And from that, I get a score I can generate. And that score will tell me how close these two records are. And whether they are matched or not, I could learn a threshold to say, if my score is above 3.3, I say it's a match. Otherwise, I say it's not a match, for example. Okay, so here we have seen the pairs, the scores calculated, and then we have the classes as matches or not matches, and so on. So the bottom gesture here just says we can use thresholds to decide on match or not match. Okay, we can in fact group into three. I can say match for sure or not match, or somewhere in between, I'm not sure. Let a human check if it's a match or it's not a match. And then we can visualize how well our system is doing. If we have data about which records are the true matches, in other words, the ground truth, then you can now evaluate your matching system to see how well it's doing. okay, because you're dealing with a lot of data. How well have you handled that data, okay, and what are the results? So again, you have scores like precision, recall, and so on. You have got other scores which tell us how efficient the blocking is, such as a reduction ratio and reduction ratio and so on. Okay, I'm going to those details here. So in data matching, large opportunities, fraud detection, as I've said, customer data integration, supply chain management. So the opportunities then, we can scale up, we can handle larger data sets to match. We can use advanced algorithms. We can do matching in real time. We can even explore privacy preservation matching. We hire a consultant to match records between hospital and clinic, but we don't want the consultant to see the actual data for the patients in the hospital and clinic. One might say it's not possible to do that, but it is possible actually to encrypt hospital data, clinic data, and still do the matching, and the matching performance will still be fine. So there's lots of research in that area. How do we preserve privacy? But it is possible. Okay. Now system software. Now system software deals with the software infrastructure, operating systems, for example, antivirus software, backup software. So when we use the computer, we use the computer because of the applications. I use the computer because I want to check my email using email application. I want to browse the web using web browser. I want to, produce documents using, Microsoft Word, check my budget using Excel. That's why we use computers. But these applications cannot work on their own. They need help of the infrastructure for the computer. The key one is the operating system. So the operating system is running for as long as the computer is running, is managing the resource of the computer. It manages the memory. We are talking about primary, secondary memory, the CPU. The operating system manages all of that because the CPU is a shared resource. There are so many applications, they all need to execute on the CPU. Who gets to use it now? Who gets to use it later? Operating system does that. The application are also sharing memory. How do we make sure they don't get in each other's way? The operating system does that. It looks at the secondary storage, the file systems, the hard drives. It does all of that. So opportunities then, if we can harness data, then we can even improve our development of this software infrastructure, including operating systems and so on. So the opportunities there. So edge computing, for example, we talk about cloud. Cloud is on the internet. We can have our own cloud-like resource. They put it at the edge of your network. That means it is closer. We don't have to go too far to access our cloud resources. We can invest in our own infrastructure close to home. So the high performance computer, I mentioned the supercomputers, we can optimize operating system support for artificial intelligence, machine learning, and other number crunching that we need to do. We can optimize the energy efficiency. These data centers we mentioned, like the high performance computers I mentioned in University of Botswana, even in South Africa, CHPC, they take up a huge amount of data. So energy consumption, very important for that to be reduced as best as possible. So studies have been done, for example, to see how can we configure our data centers, the data centers parameters. Here, for example, this was a study done on optimizing configuration of data center. Of course, that includes the operating system and application that will run in the data center. So some parameters were examined, such as which hardware should be used. We look at some parameters to do with dynamic RAM, such as the latency, the bandwidth of the memory, and so on, the cache size, the number of cores we want to use. And we see how can we optimize that such that we want to reduce the execution time for the program. So that's what I believe the audience are interested in, reducing the execution time for their workloads. But at the same time, we want to reduce the power consumption. But when we do such studies, we find out that, well, see, when you try to reduce execution time, that usually comes about by using faster hardware. That will reduce the execution time. But if you use faster hardware, then the power consumption goes up. Okay, so this was a study done by myself and some colleagues on that. So we get what is called a Pareto optimal solution, where you see a curve here known as a Pareto curve that says these are the options we can have. So the solution, not just one, but it says for a particular solution, you know, for a particular workload that we're experimenting, the power consumption will be, let's say, 43, and the other one will be 6,000. Okay. The other one next to it has got high power consumption, but less execution time, which is better for us. The third one has got even more power consumption and even less better execution time. So these two parameters, execution time and power consumption, all of these solutions, they are better in one, but they are worse in the other one. So this is called the Pareto set, and that's sometimes used to design data centers to see what sort of solutions. So I know that if my main problem is power consumption because I don't have money to pay for that, then I'll go for this solution over here, which uses less power. Okay, so we do such studies also. So that will help with the processing of data, because when we say execution time, it means we can process the data faster. Okay, but the issue is power consumption also. The study went on to look at machine learning to help us. So here we generate data to try and predict. What are we predicting? We are predicting things like cost for hardware configuration. We don't have you know, infinite data for power consumption. We can try to predict that. We do that then to design even our software infrastructure and and select configurations for hardware and so on. So there are opportunities there, because the more data we have, the better we can, you know, design hardware configurations, we can design software and so on. Okay, so here we are. We have a Pareto set also here for power and execution time. Okay, applications in intelligent systems. Okay, so intelligent systems, of course, we are all aware now about natural language processing and the benefits we get, such that the chatbots we use, maybe ChatGPT and the other ones. So if we can tackle these problems of large data sets, we're better able to build these solutions for intelligent systems, such as natural language processing, computer vision. We need to let the computer see what humans see, identify objects, and so on. I'll just pick a few of these. Recommender system to recommend products to customers on Netflix and so on. So the opportunities, we have transfer learning, for example. We can train models on large data sets and then fine-tune them on specific applications. We can use data for you know, for automating machine learning pipelines. We can have greater insight in how decisions are made. Okay, so once we're able to tap into huge data sets using the techniques we have talked about, we can do all of that. So intelligent systems also, as I said, there is overlap here. They are used in system software now. They are used in data matching and so on. So we can merge these approaches together to solve problems in these domains. Here I've thrown in a few for maybe to do with the things like spatio-temporal data analysis and so on, where we can use recurrent neural networks, long short-term memory transformers, and so on. These are powerful tools. So transformers that are used for the large language models, they are not only applicable for chatting and not necessarily natural language, but they can work with other data, as you might find for water treatment and so on. If, for example, you want to do water quality prediction, you want to process historical data to predict water quality, you know, you can do that. Hydrological forecasting, even using transformers. Okay, so it's not only about chatting. Okay, these transformers can work with all sorts of data actually. We just have to be careful how we structure the data and also how we handle the challenges of the useful transformer models being very, very large. Okay, wastewater treatment optimization. Optimize chemical dose and filtration and so on. Okay, distributed water analysis. Okay, so for example, so federated learning, we want to build models that work with different sources of data, but those sources, they don't want to share the actual data for some reason. So federated learning helps with that. So we can do collaborative water quality monitoring, for example, between South Africa, Botswana, the SADC countries. They don't want to share all the data, but models can be built that are harnessed by capturing that are trained on the individual data sets, and then they are merged together, groundwater level prediction and so on. Decentralized smart sensors. Okay, so again, I've just thrown in a few of these here, maybe to give some ideas for the audience: hydrological forecasting, groundwater contamination modeling. So I think we are running out of time, so I'll just skip ahead. But it was not really my intention to go into detail in this one, because it's just to give some ideas for those who are working in this area. Okay, so using cloud computing, big data analytics. So of course, I'm sure you have come across the Google Earth Engine also, which is a cloud resource for working with Earth data, which can include water and so on. So we can do remote sensing for water resource management, wastewater treatment performance analysis, calibration of hydrological models, and so on. All of these are possible through cloud resources also that we have available, such as Google Earth Engine. I believe some users for it are free, but there are upper tiers which one has to pay for. Okay. Now these LLMs we are talking about, we have seen their power with the chatbots that we are using and image generation and so on. Again, how are they able to do that? Because they are trained on large amounts of data. So we can learn some ideas from these large language models. We can learn some ideas from them. We have to learn about the architecture. How are they actually built in such a way that training can be done? One interesting thing that they've introduced a way to process data in parallel. The previous models also working on natural language. When they process text, they process the words sequentially, while large language models, for example, they can do things in parallel. There are other benefits they are brought about by calculating scores for example, for different words in a sentence to see which word is related to which other word, and so on, which helps in translating languages and semantics, meaning understanding what sentences mean and so on. So distributed training. How are these large language models trained? They are trained not on a single computer, but using the methods I've talked about in this talk: the GPUs, the TPUs, and so on. They are trained using huge data centers located all over the world, and they can take a very long time to train, months even. Efficient ways of basically structuring the data, compressing the data and structuring it, and then to support the users also, they need to be able to generate responses fast. So the real-time inference scaling, they can scale up to millions of users also. So the advantages for the LLMs over previous methods used for previous state-of-the-art methods used for natural language processing, the parallel processing. So I mentioned the use of supercomputers for parallel processing, but these ones actually, they can process text in parallel, and then they can relate sentences which are very many characters far apart. They are scalable. They can work with huge data sets for large-scale artificial intelligence applications. And then there are also pre-trained models that you can then Fine-tune, that means, for example, the basic model for the chatbots using transformers will just be trained to predict next words and sentences using some probability, but then they can be fine-tuned to answer questions to do it engineering or water management or whatever. They can be fine-tuned. Okay, yeah. So we can learn from the improvements that have been brought about by the large language models, such as transform. We can learn from them also. The issue of parallelism, the issue of scalability, the issue of dealing with long-range dependencies, the issue of building base models and then being able to improve them further by looking at specific tasks. We can learn from that. So the conclusion for my talk, so ability to handle large data sets is crucial in today's data-driven world. So when we understand the challenges and leverage these cutting-edge technologies, then we can unlock the valuable insights and drive innovation. So software implementations help with this. Even at the lower level, when we are implementing the software, the way we write our programs, the way we code, really has an impact on the amount of data we can process. Hardware is critical. Memory, CPU, secondary storage, network bandwidth, all of this. Supercomputers, cloud-based resources are critical for this. I've mentioned these cloud resources such as the Google Cloud Storage, Amazon, Microsoft, and so on. We mentioned, Google Earth Engine. We mentioned the use of, training large language models in the cloud. We looked at maybe some benefits of having your own hardware, and then benefits of using cloud, and also the cost of both of them. Okay, so this talk was meant to give you some ideas, hopefully, that can help with your own work as you embark on this journey of processing large amounts of data and getting the required insights and the required benefits for that, for whatever problems you are trying to solve. And so the full stack is important here. The CPU is important, the hardware, the way the software is built is important, networking is important, parallelism, how many resources are you using, what is your configuration versus cloud and local resources, and so on. I have these are just a few references, actually, just a few references that were used during the talk, but I used lots of other references, websites, and some of my own work I mentioned, such as in data matching and system software, and so on. Okay, so I'm going to stop here. I think this is the last slide, so I'll stop here. Over to you, Chair.
Thank you so much, Dr. Anderson. My name is Prof. Awufulu. I was at another presentation. I just joined. Unfortunately, my colleague, Ms. Ronell, the chair, need to quickly go somewhere, another engagement, for the department. So that's why I just decided to. She asked me to take over in terms of the proceedings. Firstly, I would like to express our deep appreciation. Or before we do that, I'm not sure whether Dr. Anderson would like to take some responses from attendees.
Yes, I'm available for that. Yes.
Yes, thank you so much, colleagues. Do you have any clarification or any point of view that you would like to share with Dr. Anderson before we close? You may just go ahead if there is any clarification, because we know with big data sets. There are substantial, as Doc, the expert, has actually provided with us, in terms of the challenges, how to navigate in terms of sometimes in terms of fake documentation, in terms of security, in terms of the infrastructure that are actually required, in handling big data sets and the solution therefrom. So if there's any clarification or points you would like to make, please go ahead, just jump into it.
All right, thank you, Chair. Can I go ahead?
Please, that's why I said, please jump into it. Go ahead.
Oh, okay. All right. Thank you, Chair. Thank you, Dr. Anderson, for that interesting presentation. I joined a bit late. I was also in another separate meeting, but I just want to quickly hear your thoughts on, you mentioned something like on transformational architectures, like when it comes to optimization of like some databases, like whereby you mentioned like some cloud databases. I'd like to hear your thoughts on the security aspects, right? With those like transformational architecture, to say like, how does it, are there any concerns like when it comes to security? And also like, I like to believe most of these systems, they do have like some cloud storage and as well as something local hybrid for sensitive data, if I'm not mistaken. But how does that play when it comes to security? Thank you.
Yeah, no, thank you for that question. With security, as we say sometimes in computer science, that if I have a file cabinet in my office, and I keep some information about students there, then the only way for someone in Germany to get that information is to actually fly over to Botswana, where I am, and come to my office and break into my office and get that information there. But there are downsides to me keeping information in my file cabinet. Maybe I cannot access it from home, or I cannot analyze that data properly because it's just on hard copy in my file cabinet. Okay, so but then if I put that information now on the network, then I can, in electronic form, I can easily analyze that information, that data, and it's also accessible. I can access it from somewhere else. So there's a cost benefit there. So for the there are some benefits to me doing things the old way, but there's a cost also. So of course, once you say information is available electronically and is on the network, then you are increasing the risk of someone accessing it. If it's in my file cabinet, it's difficult to access in some sense, but it is less useful. Okay, so there's always a risk once you say you're using cloud resources, for example, or network resources. So the more you open up the scope of the system you're using, from file cabinet, the other option, the PC in my office, which is not on the network, but now the PC is on the network, and then now you also say it will be stored in my university, but on a server in the university, also available on the network. And then you go out further to say now it will be stored in the cloud, and so on. So there are costs and benefits to that. Okay, so of course, once you store something in the cloud, if someone has access to credentials to access those resources, then they say it is possible to do that, and that is why we have had lots of high-profile leaks of sensitive data, even in U.S. government, in international companies such as Sony and so on, where people's private data has been leaked and so on, is because now our systems are more networked and so on. But there are a lot of approaches used to deal with that. So as I said, the risk is increased, but things are pretty safe for many users. For example, systems accessing data stored in the cloud may have to use particular keys. So in information theory, we have these issues of encryption and so on, where the data might be kept in the cloud, for example, but is not kept in its raw form. It is encrypted, so it is encoded. So if even someone gets that data, they might not be able to have access to the original data. For example, passwords, even passwords on your computer, they are stored in encrypted form using a one-way function. So if you enter, if you use a password on your laptop, like hello, for example, if someone steals your laptop and they see the file that has the passwords, they will not see the word hello. They'll see some encoded form of that word. Okay, so in that sense, your password is safe. Okay, people never know your password because it's a one-way function. So you cannot, you can go from hello to the encryption, but you cannot go from the encryption back to hello. So when you type in your password, it will be encrypted again and compared to what is stored, but no one will know that you use hello. So encryption is used a lot, and for that also the issue of certificates, and there are all sorts of infrastructure available like private key, public key, and so on, which make it difficult for people even to intercept communication. And as I said, even if data is accessed, it might not be in its raw form and so on. So also, but of course, as I said, the more you entrust your data to external entities, then automatically the higher the risk. So the best thing will be that if you don't want any data leaks, you just maintain all your own system. But the security is quite good anyway. The security is quite good. Yeah, I hope I've answered your question.
Thank you so much, Doc, for that. Tafila, is that okay?
Yes, thank you. Thank you, Dr.
Thank you.
Anderson.
Thank you so much. Members, do we still have, maybe we can take one or two more questions or clarification?
I just have a comment to make, Prof. Thank you.
Okay, it seems there's no more hands.
Oh, I'm sorry, I believe someone is talking. I heard someone wants to make a comment. It's just that
wonderful.
The volume was a bit low.
Please, colleagues, please jump into it. Go ahead.
Hello, am I audible?
Your volume is quite low, but I can hear you barely. Yeah.
I don't know what is happening with my computer, but thank you for your presentation, Dr. Anderson. I'm a geoscientist by profession, and I was following your presentation with keen interest. So as you were presenting, you kept on reflecting on efficiency and optimization. So all this theory, I think it resonates with the queuing theory, which is also a mathematical approach in handling large data sets in terms of processing in order to optimize the resources. So I was wondering whether there has been any prospects to, synergize big data science from the computer science perspective as well as queuing theory.
No, thank you for that question. When you say queuing theory, do you mean the traditional method that is used to, for example, calculate the waiting time that bank customers can have, for example? Is that the queuing theory you mean?
Yes, more or less the same.
Okay. Well, that queuing theory, it is used, for example, for the infrastructure I mentioned. For example, I mentioned the operating system. So operating system that's scheduling. I mentioned scheduling, where we can model the issue of processes that are to be submitted to, for example, a supercomputer, and we can work out which process should go next, such that the waiting time for the processes reduces. As I said, these are shared resources. So scheduling is very important because many people want to use these resources. So queuing theory comes there because the scheduler has got to see the queue of the jobs waiting to be submitted. And then it has to work out these things such as, waiting time and response time and so on, that you can study using queuing theory and so on. But that is traditionally done like that. But now with data science and the computer science influence on that, basically we use data for decision making. So I mentioned the issue of the car that drives itself, the self-driving car. Okay, the data is used to help the car make decisions at the intersection. Do we turn left? Do we turn right? What do we do when the traffic light is orange? And so on. So even in queuing theory, there's decision to be made. Decisions like which process should be scheduled next. For example, if you look at the bank customer, which if you have got 4 queues going for the same teller, which one should go next, and so on. So for all such decision making now, data has been used for that, because if you collect lots of data on for example, bank customers, if you are talking about bank customers, on the way they queue, the way they arrive to get service, the way they are served, and so on, then you can make better decisions about the structure of the queues and which customer goes first, which queue, and so on. And the same thing also for our infrastructure. If we are talking about queuing for the operating system in a high-performance computer, for example, the same thing. By analyzing data, we can do more. We can make better decisions regarding the queues. Even now, artificial intelligence has been introduced even in the system software, such as the operating systems. It could be in data centers or the one on your laptop. So again, decisions have to be made. So even the operating system on your laptop, it has to decide the CPU is a limited resource. Should it run PowerPoint next or Microsoft Word for the next 5 milliseconds? And the same thing in the data center. When jobs are submitted, then there are decisions to be made as far as queuing goes. One decision could be not only which job should go next, but which one should go next, and then on which machine should it run, because in the data center there are thousands of computers that run in parallel. So it's a special sort of resource allocation, as well as a temporal resource allocation, where we must decide. So all these decisions are improved by looking at data. The data comes in, for example, even if you look at the processes that are supposed to run on a data center, they have some attributes. They have certain patterns with the way they use the memory. They have certain patterns with the way they use the network. They have patterns with the way they use secondary storage. So all of these are harnessed to make better decisions for that queuing, as you put it, queuing for resources by processes. So there is a lot of work in that area now. Yes, thank you. Yeah, over to you, Chair.
Thank you so much, Doc, for that. I think, like I said, we'll probably take one more. Is there any other person that would like to clarify with our expert? Any question? One last question or clarification? Okay. I think I would like to conclude the presentation in the absence of any other comments or clarification. I would say that we've been enriched, to a large extent in terms of our knowledge with respect to challenges involving, large data sets and confirming the power of this. Some of the challenges that have been alluded to are those in terms of the security and safety, in terms of possibility of tampering and the fake data and so on and so forth. These are some of the areas that are applicable. In fact, without actually, looking at the data sets, involving, high-speed computing, even ordinarily in our daily activities, especially those of us that are doing research and storing data, we need to be very careful in terms of the way we actually, even protect our data, because some of the research that we do perhaps do have some, non-disclosure, clauses that we might actually have to ensure, safety and the security of those data. And I believe we have picked up one or two points that will enrich us in this regard. On behalf of of the SGSP, on behalf of the Directorate of Research, Innovation and Partnership Leadership, Dr. Anna Matos Goresis, I would like to extend our profound appreciation, Dr. Anderson, for taking the time, because we know to make a presentation like this at this level require, a lot of preparation, require a lot of, inputs, and especially the time that you actually, sacrifice to actually make this presentation. We really appreciate you and really want to thank you so much, because you have added value to our knowledge with this presentation. And as they always say, knowledge is power. So you've given us some power through knowledge acquisition. Thank you so much, Doctor. And we hope in the near future we'll be able to actually interact with you again. We mostly appreciate you. And to our attendees, without you, there is no presentation. You also took time out of your busy schedule, and the interest that you show in terms of actually attending, it's really appreciated. I really express profound appreciation and gratitude for taking that time, as we embark on the business of, creating knowledge, enriching knowledge, and we do it collectively, as an institution. So my appreciation and thankfulness also go to you for creating the time, because I believe we would have picked one or two, should I say, knowledge from the seminar, and this will continue to enrich, should I say, our activities, our research, and our studies as we go ahead. So thank you so much also for attending, and at this point in time, I would like to express once again our profound appreciation to Dr. Anderson. Thank you so much. God bless. Thank you, everyone.
No, thank you very much, Chair. Thank you for organizers. Thank you for attendees. It has been a great honor for me to present this, some of my thoughts on these issues at your esteemed forum, and I hope we can collaborate some more also, because I know you are working with some academics, some researchers in Botswana as well as in other countries. So I hope we can collaborate some more. Thank you very much. Thank you.
Thank you so much.
Thank you so much.
Bye-bye, everyone. Thank you.
Thank you. Bye.